Now I would like to invite Camila Senna and Mateus Ferreira. Only Camila? Come on, why don't you come? Camila, please. So we were going to have two speakers, and now we're only going to have one. Camila has a degree in mechanical engineering from the Catholic University of Minas Gerais. She is an engineer at the mining department in Latin American company. Thank you so much to the Steinert family. Okay, you are bronze sponsors. Thank you very much. Good morning, ladies and gentlemen. Today we are going to give a presentation of a case that we are exploring the feasibility of using all sorting technology in Brazil. And this correlation is related to an application that we have been using since 2016 in the Karatau watershed in Kazakhstan. So to start off, I'm going to start our a little bit about our group, Steinert Group. We have a very important pillar to use and reuse all of our resources so that as long as possible they can become resources that are finite, but we should use them in a more sustainable way, okay? And to use them as long as we're here. We are present all over the world, and our headquarters are in Cologne, and we have subsidiaries in Australia, Brazil, and in the USA. We have been present in Brazil since 2007, and we meet the demands of the entire Latin America. We have over 350 employees all around the world. So we do this global coverage. One of the main points that we have in Latin America is the know-how that we have for this kind of application of sorting software, and we are the only suppliers with a local testing center. And so what does this include? You're going to see that for this kind of technological application, it is essential for us to do feasibility tests to verify what is the performance of the ore, to see if there is application for that, economic application for this technology. Okay, besides that, we have 3 departments in our group. We don't only deal with the mining companies, we deal with solid waste from urban areas, okay, and also the ores, okay. Our technology works with detection of unique characteristics, and to do that we use many sensors, and you can see a range depending on the wavelengths from X-rays up until radio waves, okay. And what does this imply? It implies that we have the capacity to verify many properties of the materials, physical properties that are going to be correlated future with the grades, so that we can do this, so that we can enrich the material. There are other application possibilities, but nowadays I'm going to I'm going to talk about the enriching when it comes to the P205. The technology, I'm going to discuss it very briefly. There is a vibration feeder that is going to feed a conveyor belt. Along this conveyor belt, we have an area, a sensoring area, and these sensors, currently we have up until 4 combined sensors in the same machinery, and they go into the X-ray, color identification, the 3D laser, and close to infrared we have the fluorescence X-ray, and we have the induction sensor. When it comes to a mining application, what we have more are the X-ray transmission using 3D laser and induction, because this makes our system more robust when it comes to the fluorescence X-ray and the infrared. But for some applications such as the lithium, the infrared is well used, well applied, and for the fluorescence X-ray, whenever you have superficial characteristics that can be unique, so we can use it as well. But when we compare it to the transmission X-ray, we have higher robustness, okay, and also lower added value or cost. So sometimes we choose the transmission X-ray. After that, the material goes through a valve bar, and this valve bar can count on 180 valves. And then we have a compressed air, a jet, okay, that is going to change the trajectory of the material. This piece of equipment is a particle sorting material, which means that each particle is going to be identified, traced, so that we can select the particle by particle of what would be the sterile and what would be the ore. And in order to do this choosing, we have a sensor and then a decision-making part, and then the valves are going to start working, removing the material. This removal of the material is done with compressed air, and we have two exits. One that is called drop, that would be the drop due to gravity, and the other drop that is called eject, when we have the changing of the trajectory of the particle. Which do we use in the eject and in the drop? It varies depending on the percentage of each one during the feeding process, aiming to lower your overhead, okay? And using this technology, the best one would be the compressed air. When it comes to this specific process, we use the transmission X-ray, and I'm going to explain to you. And how we selected this when it comes to the signal that we have obtained. So here you can see that close to 0, 0, we have two axes. One with low energy and another one with high energy, and then we would have the total absorption of the energy transmitted. It's as if we had a part that would be a large lead part. So we would have no transmission of the transmitted X-ray. In the other system, close to the point that means 100%, that you can see is 100% of energy transmission, we would have a simple or small part that would be the total presence of the material. So no absorption of energy would take place. What we notice when we read the signals is that we create a particle that we can correlate the red with red, the green with green, and we create a separation curve, which would be a curve between the materials to be selected, denser or less dense. In this case, we used a curve to separate the denser material that is close to the superior part of the chart, and closer to the 0, 0 in the red cloud. So as the current scenario of the phosphate, I believe that you're better experts than I am. You have been working with phosphate for a longer time, but the idea is the following. The phosphate is very, very important when it comes to the global food security. And this is related to the growth of the global population, mainly when it comes to the production of fertilizers. And we have that this input is acquired from the extraction of phosphatic rocks, and it's led by China, the USA, Morocco, Russia, and Mexico. In 2020, Brazil was placed in the 6th place in the global ranking, and we have a higher production in Alto do Paranaíba and in Catalão. We can say that over 84% of the reserve extracted is used to produce fertilizers, restating the importance of this mineral. So to start off, we have a conventional processing route And we have grinding, primary grinding, secondary grinding, tertiary grinding, and then grinding again. And then we have the magnetic separation, secondary grinding, removing the sludge, flotation, and thickening. And we developed an innovation of this route, Steinert to develop this, doing the ore sorting. Ore sorting. Because it would be more interesting for you to remove the material from your processing route before it becomes tailings. And so you have better environmental conditions and also the liabilities, and then you reduce your overhead, okay? And you also reduce the processing of materials that don't need to be part of your processing, and by doing that you diminish the dilution. Another point is also for you to do some alterations in the previous process, in the mining process, if it's necessary, for instance, to have a selective mining in the deposit. And then when you use the ore sorting, you remove the dilution and you can have a mining in a larger area if this is a bottleneck. So we have many applications, many possibilities. So now we have a case study of the phosphates in the Caratau watershed. We started with this in 2016 in a pilot plant, and the main objective was to use diminish the concentration of ROM. What we found at that time in 2016, the technology was not so advanced as now. We couldn't combine the sensors, so at that time we implemented a piece of equipment only with the transmission X-ray. That's why this sensor is presented here, and also a machinery that was only 1 meter long, because it was a pilot plant. After that, in 2018, we optimized our operations, aiming to increase our capacity, our production capacity, so that this technology could get closer and closer to the expectations of the process as a whole. Currently, we went from the pilot plant and the testing phase, and we are using now the material for huge volumes of materials. They have 4 sources of materials with different sizes of the particles. They pile up this material and then they treat these materials in batches, and then they blend everything according to their needs, according to the grade that is going to be fed into the machine.
I brought here some operational results, and actually I would like to thank Eurochem for having shared this data with us. I would like to call your attention for 2 things. One is the points of the higher granulometer or particle size. I didn't see this before, but the technology has a granulometric limitation that is about 10 to 150 millimeters according to the density of the material. The most important thing is that the sensor is able to have some return and not the total absorption of the energy issued. So this top size is regulated based on that. Here, in the case of Eurochem, we have the top size of 70 millimeter and bottom size of 30 and 30 millimeters. What does that mean in low-grade stockpiles, which is one of the main points of attention and one of the main opportunities of applying this technology, because it's a material that's stocked, it's an potential environmental liability, so we can transform this stockpile that's there waiting for the cutoff or or the reserves of extraction reaching the low grade to be used, we can put that in the process route with a massive recovery around 50 or 40%, thus recovering 70 or 60 to 70% of metals in this project. And I will show this to you in a graphic because I think it's easier. We have an upgrade here. What is that? It's the increase in the grade, in the content, up to 1.43%, 1.6%, which is 46% in the increase in the grade, decreasing the amount of waste, of tailings. This leads us to believe that we are going to use the best way possible the low grade found in these stockpiles, and this will lead to all this ore that's there being removed, only the best part, and whatever is left are material with a large dissemination of this metal that is not used commercially right now. One other thing that I would like to say, one caveat. We tested ROM and the low-grade stockpile, and ROM had a satisfactory performance to them, but not as significant as the low-grade stockpile due to the heterogeneity of the material in the stockpile. We know that the stockpile material is heterogeneous, and this is one of the main characteristics for applying that technology. As a conclusion, we came to understand that this sensor-based sorting technology presents improvements for the total metallurgical recovery and also for the content of P2O5, being an innovative alternative for using materials that was not being considered for the reserves of in this case of this mining company, but this can be applied to other projects as well. An enriching of the PO5 in ROM up to 20%, between 5 to 20%, and for the low-grade stockpiles of 28-30%, maybe almost 50%. It's important to remember that all the results obtained are an average of results obtained in the operation itself during 6 months. Another very important point, due to the similarity that we have in these reserves, which are apatite rocks, we consider the possibility, a very strong possibility, of applying this technology to the deposits in Brazil, to the quarries in Brazil. Another very important point is that pre-concentration, as well as the treatment of the stockpiles, low-grade stockpiles, they show economic gain, and especially in what we call ESG, which is connected to the conditions of sustainability for the use of this waste, as well as how to dispose of this waste, these tailings. Another very important point is that in the past we didn't have such an advanced technology as we have now. So what we hope is that with the multi-sensor technology, that in Steinert is one of the very few suppliers that has that technology, for combining sensors, the efficiency of this separation process increases significantly. The ore sorting technology would increase a lot, especially using laser for compensating the signal issued by the transmission X-ray. Another very important point that is a commitment of our company Steinert is new studies with larger equipment in order to bring this technology to the reality of the Brazilian operation. So the idea is to work both in the possibilities of increasing the speed of the conveyor belt or the coverage rate for the conveyor belt and larger equipment so that we can bring it to closer to the reality that we actually find here in Brazil. Well, I guess that's it for today. Here is my contact and Lucas' contact as well. He was held back in Chile. People requested him to go there, so he unfortunately couldn't be here with us today. But he asked me to thank for the opportunity, and we do have a booth in the back, and I'm available for answering any questions that might arise. Thank you, Camila. We have time for one question. Camila, this was an excellent presentation. My name is Luis Marcelo from Copia. And you showed very clearly there is a benefit in terms of technique to operate from 30 to 70, which is interesting in terms of this technology. What I found strange was the modest results from 10 to 30. I'm not talking about the economic part, okay? But when we talk about the concentration in any scales, the smaller particle size is better. So why do you think there was such a modest result for the smaller particle size? As a limitation of the technology, we have a monolayer in the conveyor belt for a Cartesian identification of each particle, as we work with a particle sorting technology and not bulk sorting. So this specificity is needed for detecting and identifying each particle. So that's why I think that the result was below what was expected. On the other hand, however, it's easier for us to pile and to treat the coarse material that is also waste. So it's an onus on one side, but it can also be a bonus depending on how you look at it, the process and the application. Thank you, Marcelo. Now, Professor Filipov over here. Muito obrigada. Foi uma excelente palestra técnica. E eu tenho uma pergunta. Quando você comparou os resultados de Cratal e o minério brasileiro, há enormes diferenças na recuperação do P2O5. Quando você compara os resultados de Cratal com o minério brasileiro, a gente vê uma enorme diferença entre a recuperação do P2O5. Por que essa diferença? Qual o porquê dessa diferença? Não na granulometria. Eu entendo a granulometria ser diferente. Sim, nós temos diferenças em termos de depósitos e várias diferenças, mas isso é indicativo do que a gente consegue fazer em termos de exploração dessa aplicação para o minério brasileiro. O que nós temos é uma indicação. Como eu disse, a gente ainda tem que testar tudo antes de fazer a aplicação. Em termos de aplicação, eu acredito que é algo que nós temos que testar, sim, mas em outro ponto, se já é uma indicação de que a tecnologia deve funcionar aqui. É isso que a gente estava tentando apresentar, essa possibilidade. Ainda temos vários passos que a gente tem que fazer, outros testes, para poder aplicar essa tecnologia aqui. Certo, você tem diferentes depósitos, né? O de Cratal, ele é ígneo, mas eu acho que no Brasil, do ponto de vista morfológico, ele é diferente em termos de distribuição do tamanho de partícula. Talvez isso possa ter um impacto. Você tem que dar uma pensada nisso, porque esse minério de Cratal, conseguimos aumentar de 27 para 29, né? Aplicando essa questão da granulometria. Mas, fora isso, a distribuição está disponível para a separação. Sim, nós temos que fazer mais testes para entender, em termos de litologia, qual seria o impacto. Muito obrigado. É por isso que uma caracterização mineral é extremamente importante. Thank you, Camila, once again.